Okay, my name is Eunhee Kim, and I'm a graduate student in linguistics department at here UIUC, one of the committee members of ILLS6. I'm so excited to be here and to have the opportunity to introduce our first invited speaker. Professor Deryle Lonsdale had worked for 10 years in commercial natural language processing software development. He attended graduate school at Carnegie Mellon in Pittsburgh, where he received master's and doctoral degrees in computational linguistics. He joined the faculty at Brigham Young University in 1998, where he is an associate professor in the Department of Linguistics and English Language. He is also a faculty member in BYU's Native American Studies program and consults and cooperates with tribal communities and organizations in the development of language resources. Aside from his professional background, Professor Lonsdale is also a very productive researcher. His list of linguistic work includes over 85 peer-reviewed publications. To name a few recent titles here, there's Conceptual Modeling Foundations for a Web of Knowledge, Evaluating Machine-Assisted Annotation in Under-Resources Settings, and Modeling Speech Errors by Analogy. His research interests include various aspects in computational linguistics, such as cognitive modeling of language use, speech processing, machine learning, corpus annotation, data extraction, human-robot interaction, and Salish languages. Today, he's going to give us a talk about cognitive modeling of language use. Please join me in welcoming Professor Deryle Lonsdale.
Thanks. I appreciate the invitation to come here. I've never been here before, so this is a learning experience for me as well. I've enjoyed the talks I've heard so far today, and I'm glad to be a part of this conference. So I'm going to be, let's see here. I'll be talking about work that's been done by 4 different groups, the SOAR Research Group at Carnegie Mellon, the SOAR community, which is an active community of developers, including people at the University of Michigan, and 2 research groups at BYU, the XNL SOAR Research Group and the Data Extraction Group. I'm going to start by talking in general about cognition, and then I want to talk in particular about language and cognition and the types of work that we've done in the past in this area. Also a little bit about cognitive modeling along the way, and some of the applications that we're currently working on, and some of the ways that I think this research can take in the future, directions that we could follow, and then some challenges as well. So cognition generally, I've got just a big long list of things here that we often think about as linguists. What is it to think about something? What is knowledge? Different areas, aspects of knowledge, types of knowledge. What is performance? What does it mean to do something? All of these might involve aspects like problem solving, making decisions, memory, remembering things, building up skill, expertise over time, perception, and of course language is a big part of cognition. Some of the abilities that cognition has to come along that are associated with cognition are awareness, introspection, agency, the ability to plan, and also interaction with other people or other agents. Cognition is at the crossroad of a whole bunch of different disciplines, and there's been a large and growing body of knowledge about cognition. One of the problems, though, that was outlined by Alan Newell in 1990 was in a book that he published called Unified Theories of Cognition. Was he made the observation the mind is a single system. It's not a whole bunch of tiny little pieces that somehow have to coordinate. It encompasses all of the capabilities that we exhibit when we use cognition. There are observable mechanisms for tasks. We can understand the time course of behaviors. the processes that we go through when we work through a new problem, when we deliberate, and so on. We should be able to enumerate the different levels of knowledge and how they're used. And his call was to take all of the different cognition studies of little pieces of cognition and try to tie them together in an overarching framework, and then match them with experimental results, and if that's not enough, implement them on a computer as well. So this was a landmark work that ended up starting a fairly large field, I think, called cognitive modeling research. So the idea is to develop a unified theory of cognition, and there might not be one. In fact, Newell says there should be a lot of them because we have lots of different ways of viewing how cognition works. But these theories should be unified. We should try to develop a unified theory of cognition for general human cognition, human scale cognition if possible, instantiate that in a computer system, and then implement, investigate as many of those capacities as possible in terms of breadth and in terms of depth. So not just the number of capabilities, but how far we can explain what's going on with those cognitive abilities in terms of depth. But at the same time, we want to minimize the number of architectural mechanisms that we have to do that type of processing. Well, this area of research has produced a whole bunch of different architectures. There are different cognitive modeling systems, different algorithms that are used for different areas of cognition, and I'm not going to pretend to try and give you an overall view of this whole area, but pursue one particular thread that I've been working in quite a bit, and that's with a system called SOAR. SOAR was initiated by Alan Newell and Herb Simon and some students at Carnegie Mellon since the mid to late 1980s, and it's been ongoing ever since. SOAR is a symbolic rule-based system. It's based on the theory that Newell laid out in his book. It's instantiated as an agent architecture with all of the implications that there are for agency and so on. The system is able to input information from the outside world and output information to the outside world. When it tries to solve a problem, it uses a goal structure, and if it can't achieve a goal, it tries to break down the overarching goal into smaller sub-goals that it might be able to solve along the way, and in the process learn how to do that solving. It can learn from the tasks that it executes. It's a machine learning system. It can program itself, if you want to think about it that way. And it's an open source program that runs on multiple platforms. So there were some interesting early applications of this SOAR architecture to problems that involved some kinds of cognition. So blocks world, getting a computer to figure out how to build certain configurations of blocks on a table. Doing medical diagnoses. A team of, I don't know if you've heard of RoboCup, but it's a competition of teams of robots playing soccer against each other. One of those teams was controlled by SOAR agents. Each of the team elements was controlled by a SOAR agent. Modeling air traffic control, intelligent pedagogy, those types of applications were ones that involved a SOAR agent running to accomplish these tasks in either a virtual or a real environment. How do you evaluate how well any of these types of systems are working? Well, one of the questions is, does the model actually do the task that it's programmed to do? Does that task performance match what humans are doing if we want it to be cognitively plausible? What does the agent learn? How does the agent learn? And how can these results be generalized or extended beyond just the small task that it was designed to do? Well, he said some interesting things about language, so here's where we get to the part that I think we're most interested in. Even though Alan Newell was very upbeat about the possibilities of doing cognitive modeling, this is what he said about language. I've just got 3 quotes for you here. The first one says, "There's no question that language should be modeled. Yet I demur from simply adding it to the list. Language should be approached with caution and circumspection. A unified theory of cognition must deal with it, but I will take it as something to be approached later rather than sooner." The second quote is, "Language is a central feature of human mind-like activity. I have stayed away from theorizing about language because I find it formidable in terms of the collection of results that has accumulated and the degree of controversy that seems to attend competing views of linguistics." And then finally, the third quote, "There seems to be no way to enter the linguistics fray with a little theory, even a highly approximate one. To do so is to invite the wrath of the linguistic gods, full-blown from the brow of Zeus or nothing." And I think we can all appreciate the points that he's trying to make there. Well, as a grad student at CMU at the time, what do you think we did? We thought, gee, what are we going to do? Wait until the field of linguistics is more amenable to doing modeling research? Should we just watch from the sidelines and cheer the cognitive modelers on and interject relevant suggestions every once in a while? Should we experiment with just small portions of the cognitive modeling space that have to do with language and let those other guys do the other things? Or just directly dive into the fray? Any thoughts about what you would do as grad students given that situation? Well, what we did was we kind of took number 3 here. We said, let's experiment with at least small portions and not try to do everything all at once. So what we did was we tried to take the unified theory of cognition, or a unified theory of cognition, as specified by Newell, and the cognitive modeling system SOAR that had been the instantiation of that, and then add our own language-related components to that system so that we would come up with what we could think of as a unified framework for overall cognition, including natural language, and we call that NL-SOAR. So what does it do? Well, it can convert input sentences to linguistic structures, syntactic and semantic. We call that comprehension. It can convert linguistic structures to output sentences, generation. It converts linguistic structures between 2 different languages, mapping between semantic representations, for example. Manages a model of discourse, participants, and reference, and ongoing situation, the common ground, and so on. And it can take pieces of these and put them together compositionally. And it models interaction with language and other tasks that the agent can do that aren't language tasks. So I'll give you some examples of those. Some of the early applications were, and I'll talk about the first bullet item in some slides in a second here. So some of the human parsing performance work that was done by Rick Lewis for his dissertation was showing where humans in parsing English break down because even grammatical sentences can be so complex we can't handle them. And the system is able to break down at exactly the right place, or be led down the garden path and not be able to recover. Or in cases where we are able to recover, backtrack and figure out how to resolve those ambiguities. There was also a system that modeled the acquisition of English determiners by Polish speakers. And there was work on simultaneous interpretation, modeling somebody who would be a simultaneous interpreter, taking English input and outputting spoken French and doing all of the other tasks that someone that does simultaneous interpretation does. Here are a couple of other examples. One of them was the NASA test director. This is the last person to clear the shuttle before it launched. And the test director had a fairly complex task of hearing reports from all of the components come in, and he would track through a set of protocols whether each of those tests was succeeding. And if they all did, then he would approve the launch. Well, it involved lots of different tasks. Whoops, I'm sorry. Like, trying to find the pointer here. So these are actual speech protocols of the reports as they came in that they would be listening through. We had eye tracking information on so they would be following in several 30-some huge binders of several pages of printed material that they would just read through as they're following the task. And so we had eye tracking information on that, page scanning information, as well as receiving auditory input, understanding it, comprehending, generating appropriate responses, and speaking them. And so by putting all of these together, using all of the technical details in the SOAR system that I'm not going to go into in this talk, be able to kind of interleave all of these different tasks in what looks like a plausible accounting for what's happening at all of these different levels, language and non-language tasks. Another example is what's called an I4 agent. I4 stands for Intelligent Forces. this is a system that can fly a plane or a helicopter or other unmanned vehicles. It has to know about geometric reasoning and mapping and battlefield tactics and flying the aircraft and so on. We didn't have to program that. There are other people who know how to program agents to do this information. But the agent is able to take in sensor data, figure out how it relates to the task, and perform actions depending on that. Internally, this is where the agent part comes in. It needs to know about itself and about the enemy, a model of the enemy, and what its mission is. And it's able to incorporate all of this into one central system. What we were able to do was add to that language components so that it's able to comprehend incoming language, in this case communications over the radio link, and do reasoning, understand all the words, and do semantic and syntactic and discourse reasoning about the situation, using the different linguistic structures that we have in there, and formulate proper responses when necessary, and send them out on the radio comm back to either the other human or the other agents who are talking to them. So in one architecture, we're able to do all of this work. So this is an example of what we're able to do by combining those together. Well, so what did we do? So this brings us up to about 2000. So there were some interesting and complex SOAR applications that didn't involve language. Flying planes is pretty cool, or tracking other types of tasks that they do, robotic teams, for example. A few of those we were able to have NL-SOAR implementations. Mostly these were integrations with SOAR agents doing these other tasks. All of these had very limited lexicon, very limited syntax, not much in the way of semantics, just enough to get those small tasks that I mentioned done, and a little bit about discourse. The discourse structure is really important when you're in battle and in combat and so on, but it is relatively restricted compared to what we do every day. These included thousands of rules, and we were able to do this for English and French. Recently, there have been some nice enhancements to the basic SOAR architecture developed by mostly the University of Michigan and reported recently in a book by John Laird, including semantic memory, episodic memory, both of which are really important for language, and you might wonder how we're able to do anything without them. Well, now that we have those abilities, it's going to be a lot nicer. It also has reinforcement learning and a tighter interface with perception. So this is just on one slide what the architecture of the system looks like. Essentially, it's got three types of memories: procedural memory, semantic memory for long-term facts, and episodic memory where it can remember and think back on episodes in the past. All of these can be learned over time, but for language, what's really important here is the working memory. So we all, I think, have studied a little bit about working memory. SOAR has a central working memory. All of the tasks have to be funneled through there, and that gives you the ability to model a little better what humans are doing the way humans would. There are also memories for visual long-term memory, mental imagery, and the agent can receive perception from the outside world and perform actions that go to the outside world, whether it's a robotic body or a virtual environment or something like that. All of this is open to inspection, so you can actually trace anything that's going on. This is not a big black box. It's a glass box where everything can be followed really nicely. Well, more recently, the SOAR people have done things like developing virtual humans for scripting or counseling people or language pedagogy. These agents have been put into certain online gaming situations where you can play against one of these agents, and it can even learn your strategies and use them against you. It's kind of interesting. Modeling whole organizations and even large level, even country level situations that might arise as you put together thousands of agents and give them each their own sphere of activity and influence and so on, and then watch what happens as it emerges. Similarly with crowd behavior and swarms, even geopolitical scale modeling, and also, as I mentioned, robots and unmanned vehicles. Well, what about NL-SOAR? What have we been doing since about 2000? One of them was that we were able to integrate the system with WordNet. So now the system knows everything that WordNet knows. All of these, all of the lexical words, all of the relationships between, so on. which reduced sizably the number of rules, because before the lexicon had to be hand coded with if-then rules, and that was onerous. It kind of made sense to load into semantic memory the entire WordNet content. I also developed a system called AML-SOAR, which allows SOAR to do analogical modeling. I understand you'll be hearing from Royal Skousen in a couple of weeks. So it was an implementation of that. As I'll report in a few minutes, we implemented various syntactic parsers and various semantic representations, and we've continued to integrate with other systems. So I'm just going to talk about that for the rest of my talk today. One of the things that we've worked on is clinical trials. So anytime a drug has to be tested, people have to be enrolled to do that. You want people who meet certain criteria, enrollment criteria. Well, there's a government website that has all of the eligibility requirements for all of these upcoming clinical trials, which is really nice. Unfortunately, they're not in completely grammatical English sentences. They're sentence fragments and so on. So traditional parsers don't work really well for doing that. But we were able to do is parse out this information and in a particular format that I'll mention in a moment, convert it to what's called discourse representation theory, and have these first-order predicate calculus statements that can be matched against patient records. And we were able to match them against patient records and make recommendations to doctors which patients of theirs might be eligible for certain clinical trials. They have a stake in doing this because they get usually kickbacks for doing this. And so doctors are really interested in pairing together their patients with clinical trials. Another example is human-computer interaction. So we are able to have a human speaking through a speech recognition system, Sphinx in this case, and it sends the words to the agent, the SOAR agent, which understands, builds a model of the dialogue, and generates appropriate responses through text-to-speech. So a human can talk to one of these agents, a robot or system or whatever. And in fact, we've even had two agents talk to each other using English. It's kind of interesting to see what happens when you put them together like that. A recent application has a human guiding a robot through tasks, maybe tasks that it's never done before, by the way, the robot is controlled by SOAR, so we were able to take our language components, put them in there, and the human guides the robot through a language acquisition process, acquiring the verbs and prepositions and nouns and so on during the task that it needs to know to be able to perform tasks and learn new tasks, so that you don't have to program the robot in a computer programming language, but instead you can use language and natural interaction to build up task abilities in the robot. So what do we do for syntax? Well, in the 1990s, it was based mostly on government binding principles and parameters using an X-bar representation. For the last 15 years or so, we've used also another parser called the link grammar parser, and I'll say more about that in a moment. In the last 10 years or so, we've been working a lot with minimalist syntax. We've extended the agent's ability. Now it can also handle Japanese. We've greatly increased the complexity of the types of sentences it's allowed to process, and we can build incremental visualization of the models that are being built in the system with a system called GraphViz. So the question is, which parsing strategy should we implement? I mean, what's the best to use? And the answer is, it depends on the task. That's what we're finding out, of course. And linguists probably already know that already. So in terms of our minimalist parsing, we're interested in complexity and looking at the complexity of sentences. So these are just a couple of English sentences, one where there's no ambiguity at all, but fairly complex structure, a ditransitive. This is a sentence that has all kinds of potential ambiguity, lexical ambiguity in lots of different ways, and so we're trying to track how much working memory is being used, and when can we count on not unused fragments being decaying away and so on, and making use for making space for other tasks. Just to show you, these are sentence parsers from Japanese. You can see the heavy left branching structures here, as opposed to English on the right. So on the left we've got Japanese sentences, and the English right branching, and so on the right we have an English sentence here. But one of the problems is that a lot of the tasks that we're working with have ungrammaticality, exhibit a lot of ungrammaticality, or at least not what we would think of as being grammatical in a typical linguistic theoretical sense. L2 learner English, for example, or spoken language, controlled language in some, I guess you could say, corporate or military situations. Just parsing headlines ends up being kind of an interesting task, and there are people interested in extracting the content from headlines, or PowerPoint slide bulletins and so on. Well, traditional parsers don't really handle these types of language really well, and so we use, for these tasks, we use what's called the linked grammar parser. It's fast and robust, and it works where these other parsers don't. It's not really based on linguistic theory, but it does show relationships, undirected relationships between word pairs, and so each relationship has a label like subject and verb, or verb and object, or preposition and object, and so on. You can score the links with variable scores and penalize certain types of linkages and so on. So we've been able to use this, for example, for grading essays of English learners. There are a lot of mistakes. Typical parsers don't work really well. And so what we've been able to do is send essays through the linked grammar parser. And here's an example of a perfectly good sentence. I've been majoring in material engineering at my university in Korea. Works really well. On the other hand, here's one: the class most important is mathematical for my. So that's just not going to parse really well with a traditional parser. But the linked grammar parser at least tries to piece together things and jettison information that doesn't seem to help in the parse. And so it knows that it's talking about a class and it's mathematical, but the rest of it doesn't really know. We've been able to pretty well correlate our system's performance, doing a little bit of reasoning beyond these parses with the performance of human graders. Also in other domains, so here's a domain that we're interested as well. This is a biography, so somebody wrote, Mary married, I think, 23 November 1661, Samuel Gay. Kind of weird syntax, but at least the system, if it knows that here's a date and here's a marriage between this person and so on. We've also developed linked grammar parsers for other languages, so for Persian and for Arabic. What's nice about the linked grammar parser is it'll give you multiple possibilities if there's ambiguity. And I've even worked with Salish languages for my own purposes, developing a linked grammar parser. But once we have this parse, then the system can do reasoning on the types of relationships that are here, and as we'll see, develop semantic representations and so on. So what types of semantics have we implemented in SOAR? Early on, we used what were just called annotated models, which were essentially just recursive feature value structures or attribute value structures. Later on, we worked on lexical conceptual structure, used that as kind of a framework, not completely, but the basics at least. And I've already shown you an example of discourse representation theory. We've also used first-order predicate logic, and recently we've been experimenting with cognitive semantics and also cognitive construction grammar, which are two other theories that have a lot to do and to say about embodiment and spatial orientation and so on. And of course our agents are kind of attuned to that type of information, so we're interested in the connection between those. The semantic processing is incremental, and we can even interleave it with the syntax, so we don't have to wait until all the syntax is done, and we don't have to wait to do syntax until the whole sentence is received. We can do incremental processing, and we can interleave syntax and semantics along the way. And we have also visualized the semantics in SOAR as well. So these are examples of our LCS representations for sentences. Typically, essentially, they're undirected graphs that have concepts and relationships between them that are labeled. And we represent all possible word senses. So here's an example of a sentence that has all kinds of possible word senses, and the system has to choose which one of these is the most appropriate for the situation. So it does a fair amount of reasoning to be able to come up with that. In terms of cognitive semantics, we can use image schemata as a form for representing the lexical semantics and the pragmatics that are associated with elements in a sentence. So here we've got an image schema for knife, and with information about the domains, and the parts. So a knife has a certain spatial form and a directed form and perhaps prototypically a color and so on. And over here we can compose these image schemata in interesting ways. So a knife is used for cut, and it has a relationship in the domain of silverware, and which in turn has other parts and so on. So we can build these up. What's also nice is that you can take conceptual primitives and compose them together by reading the syntax. So the system knows about basics, like above has a trajector and a landmark and some type of vectorial orientation, and it's got a representation for a table and what a lamp might look like. These are just kind of cartoon representations, but it shows that what the system is able to do is when it has a prepositional phrase like above the table, it's going to say, okay, I know I have a table is going to be the landmark, and then there's going to be some trajector above that. So when we say the lamp above the table, now the lamp is going to replace the trajector placeholder, and we have a spatio-visual representation of the content of that prepositional phrase. This can tie really nicely and directly to the visual system, and it can represent things that it sees in its visual field. We're also interested in looking, as I said, at information from a textual perspective. So here's an example from a book. There are thousands and thousands of books of like these online that haven't really been processed for information yet. This is talking about a woman named Myra Harwood, who was born in 1835 in Vermont. She married Elijah Spencer. It talks about their children. It says Elijah Spencer died in the Union Army in 1863, and his widow, oh, who's the his? Elijah Spencer. Who was his widow? Well, you need to know about what a widow is, and then she married Jonathan Squires, by whom she had one son. Very complex syntax. And by the way, this is like only one or two sentences, so again, parsing this with a typical parser would not work, but we're able to send this through the system and extract information, multiple mentions of the same person, and recognizing dates and places and so on, and matching them with an ontology. An ontology is a user-specified constellation, if you will, of relationships and concepts that the person is interested in extracting from the text. Without having to program a computer to do that. We have a system that can take this ontology and look for this information using the parsing that we submit the text to, if you want to think of it that way. So again, SOAR is a component in a much larger system that does the linguistic processing, but sends the information downstream so that an ontology matcher can match all of that information and put it in a form that people can query easily in a database. So it can take a sentence like this, and we use the link grammar parser, so this is what the parse would look like. And then we're extracting, essentially using cognitive construction grammar, the dates and what we call living events or life events, and point them to a referring expression, which is in this case the subject of the sentence, and which we know as a person because of the way it's been identified by the link grammar parser and the semantics of this particular type of construction. And then we can even abstract away and just get the life events and the people and the dates and names and so on. And so here's the next sentence in that big long in the big long example, where again we're extracting from another sentence the same types of information, and then coming up with the targeted information that people are looking for, including the persons and the relationships between them. And what's really nice is that we come up with a schema, an abstract schema of the content, the semantic content of this sentence, and a sentence that looks completely different in terms of syntax, in terms of length and everything else, still has kind of the same underlying semantic schema, the same underlying ontology. And so we're able to match those together and extract that information. Well, you might ask, where's all the cognition in all of this? Most of these tasks have been fairly narrow. Most don't directly model human data. But we are building blocks. We do have these building blocks that are more useful for, I think, a wider scale implementation. We're still building and exercising the scaffolding for language in these types of agents, and there's a wide variety of tasks that we're working on. Meanwhile, we're collecting the data, we're elaborating the models, and other people are collecting data. We saw good examples today of data that's been collected on human performance with, in the realms of phonetics and morphology, and those will be useful because we want to be able to incorporate all of those into a more comprehensive framework. So, for example, one of the things that our agent can now do is resolving prepositional phrase attachment where there are ambiguities. I saw the man with the telescope, right? The typical example. With the telescope attached to the verb or the noun. Well, the system is able to do some reasoning now and figure that out. We're able to load into it lots of examples that have already been annotated by the syntactic modeling research community, put those into the agent. The agent can use that, including for instances it's never seen before. This is another type of ambiguity that turned out to be really interesting that you don't see much in the linguistic literature. So this is gerund versus participles. So my favorite cousin was singing versus my favorite activity was singing. Identical syntax in terms of word structure, but completely different in terms of the internal structure. Things like this we don't think about, but the agent has to be able to sort through. And so in our case, we've been able to have it do some reasoning about cousin and singing. Do cousins sing? Yeah. Is singing a type of cousin? No. So then we can probably assume that this is a participle, whereas my favorite activity was singing. Is singing a type of activity? Yeah, it is. Where do we get that information? WordNet has all that information. So there are all kinds of different semantic measures that the agent can use to try and figure out what's the best way to resolve this structural ambiguity. Recently, we've been working with episodic memory. So garden paths are the types of sentences that we end up not being able to parse. We're led down the garden path. That's why they're called garden path sentences. Well, what typically happens is we parse it, and then we say, oops, and then we go back and try to reparse it again and remember where we went wrong so we don't go wrong again. That's what the agent, now that is capable of using episodic memory within the last couple of years, we've been able to tell the agent, okay, parse a sentence like you normally would and store the episodes, now that we can store the episodes. And then when you hit the garden path, when you realize that you've been led down the garden path, recognize that your parse is untenable, and think back and identify which episode was the one that was problematic and led you down the garden path, and then reparse the sentence, but don't use that path. Use a different path. And we were able to show how we can use episodic memory to recover from these garden paths. Well, is it time yet? I've got an alphabet soup here of a whole bunch of different conferences. The point is that there's a lot of human performance and behavior data that's being collected in linguistics as well as in the other areas. So cognitive science, the mental lexicon, the sentence processing conference, language development at Boston University. All of these have people who are reporting on language behavioral data. We saw some examples today again. There are also a lot of modeling applications, as I mentioned. I've just kind of focused on one today in my talk because that's all we have time for. The field is maturing. There are several different conferences that talk about intelligent agents, cognitive modeling, all of these types of areas, not all of which address language. Many of them don't address language for the very reasons that we talked about earlier on. That's a hard thing to do. It's a huge topic. How can you possibly make any claims about doing anything? But there is more cooperation between cognitive science or the cognitive modeling communities and linguistics, computational linguistics, natural language processing. So there are a couple of conferences or workshops that focus in this area and try to bring these communities together. One of the questions to ask is human-scale cognitive modeling necessary to be able to do this? Do we have to wait that long? Is it possible? Is it even possible to model the cognition of a human? Is it desirable? Is it irrelevant? Should we just be doing this anyway as linguists? These are, I think, questions that we could wonder about. So I couldn't help but noticing in a recent job ad put out by another university, one of the points was new advances in computational modeling and machine learning, along with new sources of behavioral data, are opening up opportunities to build more complete and accurate models of intelligent behavior. And I agree with that. I think that's nicely put. I think there's an increasing amount of interesting work that's being done on cognitive modeling in general, and increasing information about how we process language, that there's enough information that these two could be brought together in interesting ways. So I think there's a lot of work that needs to be done. I think the field is moving quickly. There's a lot of work to be done. There's information accumulating quickly. And so I'll ask again the question, what should we do? Wait until the field of linguistics is more amenable to cognitive modeling? This is the question we asked 15 years ago, 20 years ago. Watch from the sidelines and interject relevant suggestions every once in a while. Experiment within small portions of the cognitive modeling space, or dive directly into the fray. I'm still not prepared to dive directly into the fray. But I think if we choose any one of these two, we're really not doing what we could as linguists to help inform the research on cognition, because language is such an important part of cognition. And we would do that at our own peril, because I think we need to understand what's going on in the area of cognition, so that can inform us in our linguistic theory, in our language processing applications, in our own research, in our collection of data, and so on. So I think that's about all I had today, but I thank you for your attention and hope some of that made sense.
Almost 20 minutes for questions.
Hi. So would you be able to give like a couple examples of the types of relationships that are output from the link grammar sort of parser, like, and how, or particularly the ones that would be different from a dependency graph you'd get from like the Stanford parser?
Yeah, okay. So let's talk about dependency parsers first of all. The main difference between the link grammar parser and dependency parsing is that the link grammar parser has undirected arcs as opposed to directed arcs. And the links between them are not really linguistic theoretical. This was put together by people who are computer scientists who said, we're really not interested too much in linguistic theory. Let's just try and see, they put labels on there that we could interpret as linguists as subject-object, or subject and verb and object and so on, but not in any way that is as directly tied to a linguistic theory as dependency grammar or dependency parsing is. The problem, you can run sentences like the ones that I've shown you, the ungrammatical, so-called ungrammatical sentences, through some of the other parsers like the Stanford parser, but you're just not going to get the types of information that, in all cases, that's going to be, I guess it's just not robust enough to handle some of the relationships that we're looking at. And so I'm not claiming the link grammar parser and it is in any way cognitively inspired, and the developers wouldn't say that either, but what we're able to do is do reasoning about those parsers in a way that makes a lot more sense than, kind of interpreting that information into a way that we can make actionable in a way better than we can with other parsers. Yes?
Yeah, so this is really interesting. I don't know very much about computational modeling, and this could just be my ignorance, but it seems to me like what I've read about it tends to kind of like prove or back up a lot of construction-based types grammars. But I don't know, would you say that your model has grammar?
It depends on the task. So as I said, for certain tasks, we use the linked grammar parser, which I guess from a linguistic point of view doesn't have a grammar per se, although I have a student right now, some of these slides about construction grammar, cognitive construction grammar, is he's actually trying to directly implement that particular approach from the linked grammar parse to get a semantic representation that follows kind of what some of the claims are about cognitive construction grammar. So there are, I guess I'm still at the point where I don't believe that any one particular system is going to work in all situations, which raises the issue, you know, what do we do as humans? You know, do we have a different grammar that we use when we parse things, that sentences or utterances that are not standard grammatical? Do we just use probabilities? I mean, what's the proper way to think about this? I don't know the answer yet, but it may be some combination of a whole bunch of different strategies. And if so, that's an interesting question for linguistics, right? How do we reason and choose between these different strategies? That's the type of thing that I think is really I'm interested in modeling. I haven't implemented all of the syntactic theories that I know, for example. I may at some point, or I may not. But it would be interesting to see to what extent different theories work for different types of tasks, if that makes sense. The minimalism, for example, the parser that we have for minimalism would not work with this genealogical information with these horrifically difficult convoluted sentences. The linked grammar parser is much more amenable to that. The linked grammar parser is not really good if you've got nicely grammatical sentences and you know, they're short and you want to deal with all of the ambiguity and so on. So it kind of depends on the task, which is part of the solution and part of the problem.
Thank you very much for the wealth of information and the very complex systems. So I'm very interested in the parsing for the second language writing. Mm-hmm. I wonder whether you can comment more on how do you deal with the say, dangling words or ungrammatical sentence, or figuring out the most structure you can. And the other attached questions will be, how does that differ from the garden path processing? We see there failure, right? You have to recover. So it's just some wealth of questions. So I was wondering whether you can explain more.
Okay, those are excellent questions. First of all, the one about grading student essays. There are some interesting observations that we had from doing that work. One of them was that typical grader, you know, there are other systems that grade student essays. They use a lot of global features for the essay, number of words per sentence, number of correctly spelled words, and so on. We were interested in looking more at the grammatical structure, and which is why we use the linked grammar parser, because it can, you know, if it's going to fail completely, we know there's something really, really wrong with the sentence. So we score each sentence individually and then come up with a comprehensive score for the whole essay. One of the issues with student grading is that a lot of students will not create sentences. They'll just write and 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 not create sentences. The sentences will be, you know, what we would think of, we would break them up into 8 or 9 different sentences. They just keep running on, run-on sentences, right? Typical parsers have real problems with that. The linked grammar parser is a lot more stable in those types of environments. And it will also handle spelling mistakes. There are a lot of spelling mistakes as well. One of the problems that we had with the grader was that it only did syntactic processing. It didn't do much with the semantics. And so you could have a perfectly grammatical sentence that was completely nonsensical. Yeah, colorless green ideas sleep furiously. It would score that as a perfectly good sentence, but since it wasn't doing any semantic processing, it would give a much higher score than a human scorer would. Now, one of the other issues we found was that the computer was a lot stricter than the humans were. So in an essay that was pretty much grammatically grammatically correct, but had some errors in it. If the errors were kind of minor, we compared our scores against the human scores, and the humans would score it a little more liberally. Well, they got it, they missed this construction or whatever. They forgot the apostrophe in this genitive construction, but that'll be okay. Whereas the computer was a lot more unforgiving about the syntactic structure. And so as a result, the computer scores tended to be a little bit lower. But it was also the case that the humans would be a little harsher on the student if they came up with these nonsensical sentences, whereas the computer was a lot more generous in those situations. The last thing I would mention is that, well, I guess that, the other question was about the garden path sentences. Yeah.
My question,
yeah.
the question as I imagine it,
yeah.
Garden path is like you find that you fail at a certain point.
Yep.
So how is it different from the processing of, say, language learners?
Yeah,
right?
So that's an interesting question. We didn't use any garden path processing to try to understand what these students were writing in these student essays, because that was done quite a few years ago, and we didn't have episodic memory yet. So that would be kind of interesting to go back and say, let's see, that sentence tried to parse it, let's go back and try something else. That would be an interesting exercise. One thing that the theory of garden paths is really interesting. I mentioned Rick Lewis wrote a dissertation on this whole topic, and he focused on English, but then he showed how the architecture that he came up for to predict when a sentence will be a garden path or not transfers to other languages. So he looked at other languages as well, and we just had a student look at garden path sentences in Japanese. Japanese is kind of interesting because you've got case marking, and so in structures that would be ambiguous or would cause a garden path in English, they end up not causing a garden path in Japanese because you've got the case marking to tell you this is a topic or a theme or a subject or whatever. And so and the system was able to deal with that aspect of garden pathing in Japanese as well. A lot of work to be done though in that area. I should mention we haven't done anything with phonetics yet. We had a student working on getting a speech lattice from a speech recognizer input into the system so that it could maybe resolve some higher level ambiguities that you get in speech. We've all used Siri or whatever, and it comes up with crazy words that really don't fit. That's still a work in progress, but we think kind of interesting. Yeah, Sphinx. All right. Thank you very much.